Hello, everyone. Nice to be here today. Today, I'll be presenting our work, Llama-Nemotron, where we build efficient reasoning models. So Llama-Nemotron is NVIDIA's effort to build open and efficient reasoning models. And they come in 3 different sizes. We have Nano, Super, and Ultra. Nano is geared towards PC and edge. So it's a 8 billion parameter model. Super is 49B, supposed to focus on one single data center GPU. And Ultra is for multi-node inference. So these models have very leading accuracies. And they also offer a reasoning toggle. So you can either turn the reasoning on and off. And these are completely open source with open data, open code, and open weights. And they are enterprise ready, so you can actually just deploy them right away. Llama-Nemotron Ultra, what's the catch? So it outperforms DeepSeek R1. Here is artificial analysis index, which benchmarks models from leading developers. And you can see that Llama-Nemotron scores 61 on an aggregate of a bunch of these benchmarks compared to DeepSeek R1, which scores 60. We've seen a recent rise of reasoning models, especially by OpenAI O1 and of recently, earlier this year, DeepSeek R1. So these models think before giving an answer. Usually, when you talk to ChatGPT, you'll give a question and you'll just directly get an answer. But recently, these models, before giving an answer, they will have a reasoning trace, here shown in think tags. So given a question, you'll have this reasoning trace and then an answer. So more time is spent during inference time. Roughly 10x more tokens are generated by these models. So if ChatGPT earlier would output, let's say, 1,000 tokens to give its answer, now it's spending 10x more tokens to give you the answer. So what does it do? It unlocks superhuman performance on a bunch of challenging domains like mathematics, coding, complicated science questions. What's special about these reasoning traces? So these reasoning traces are akin to how a human would think about an answer before giving an answer, and it has complex thoughts. There is self-verification. The model has some complex thought and verifies whether it said it right or wrong. It backtracks on things it thinks is wrong. There's multi-step inference, and it has reflection as well. Let's motivate reasoning models by this interesting example. Let's say your question is, write an efficient Python function to check whether a number is both prime and divisible by 5. Let's see what the non-reasoning model does. It writes 3 functions, one to check whether the function is prime, second to check whether it's divisible by 5, and then the final answer it calls is just calling both of those functions and checking with an AND operation. Now, this is technically correct, but highly inefficient. On the right, we have a reasoning model here, which thinks about the question. And in green, you can see it comes up with the thought. So the only number that satisfies both the conditions is 5. So it's smart, clever, spends a lot of token. A lot of thinking tokens were used, but it arrives at the correct answer, which is just to check whether the number is 5 or not. So what is essentially these reasoning models? It's essentially to use more tokens to arrive at a better answer, in short. On the left, you have our Llama-Nemotron Super 49B model with reasoning off and on. On the y-axis, we have the number of tokens spent to come at that answer across a bunch of domains. And on y, you have 3 different benchmarks. You can see in light yellow, the reasoning off model thinks maybe for maybe 1,000 tokens. And the reasoning on model spends a lot more, like an order more tokens. And consequently, the accuracies are also much better. On the right, we have our plot by OpenAI, where on x-axis you have the time spent in compute, and y is accuracy. So it clearly establishes a new scaling law. The more time you spend at inference, the better accuracies you get. Now, how have these abilities come up? In the last year or so, we have seen this explosion of reasoning models. And the models were not able to achieve these capabilities before. So the main trick which got us to this was reinforcement learning with verifiable rewards, in short for RLVR. So this paradigm is pretty simple to understand. This is enabled with reinforcement learning, and all you need is a very cheap verifier. So this is only possible in domains where verification is easy. Like the classic computer science question of P versus NP is, generation is hard, but verification is easy. So in all those domains where verification is easy, we can do this loop. So given a prompt, the language model policy will generate a response. And if we have a cheap verifier, which can evaluate that response and give either 1 for a correct or 0 for a wrong answer, and then the model LLM policy can use that binary reward to just improve itself. And the LLM policy already is pretty smart. It has all the reasoning, all the knowledge from the world with pre-training, and this is kind of like the key to RL. RL, we were just starting from scratch, probably doesn't work, but starting from an already good enough model actually can get this RLVR loop to work. So what does this RLVR training allows us to do? So DeepSeek R1 open sourced all of the techniques that they use to arrive at these reasoning models. On the left, they plotted how many tokens the model outputs as you train more and more with RLVR. You can see the number of tokens explodes with this training. And consequently, on the right, accuracies on these hard benchmarks like AMI also increases. Now, why is RLVR so hard? All of LLM pre-training or even supervised tuning is all parallel at once. You have all the data, and transformers are essentially just training all in parallel. So it's teacher forcing, so everything happens in parallel. But in reinforcement learning, the third stage of response generation is very expensive. You have to do it auto-regressively. You have to do it one token at a time. So this makes it much more compute intensive. You have to, let's say, generate 10,000 tokens. You have to do it like 10,000 steps at a time. So LLM pre-training or SFT is parallel, but inference and consequently RLVR is sequential. Okay, now that the background is set, let me describe to you how we use these tricks to come up with Llama-Nemotron, a series of models. And they are comprised of 4 stages. First, we start with the base model, and stage 2 and 3 are about imbibing the model with reasoning, and stage 3 is about polishing, which is the RLHF paradigm. Now, we have to start from some base model. So NVIDIA has their own base models as well, but we wanted some models with strong industry adoption. So that's why we chose the Llama 3 family. And also, they are much easier for enterprises to work with because these are non-Chinese models. So that's why we started with the Llama 3 family. I know Llama 4 is out, but this work was done before Llama 4 was out. So now reasoning models produce 10x more tokens at inference. So we probably need to optimize these models for inference. They're not as fast currently. So that's what we do. We essentially take the 3 Llama models, 8B, 70B, and 405B, and we just optimize them for inference. The details on how we optimize it is in the technical report. I'll skip that for quickness here. So we shrink the 8B down to 4B, 70B into 49B, and 405B into 253B. So interestingly, the 405B doesn't fit on a single node, but 253B now can fit on a single node, and we increase the throughput by 1.7x, and for 70B by 2 to 5x. Now, these are some of the details, but it essentially involves neural architecture search and some distillation to come at those faster models. Now, I'll jump to the supervised fine-tuning, which is the stage 2. Now, once you have a base model, how do you imbibe the model with reasoning? Like the way OpenAI O1 and R1 did was essentially to do RLVR and a lot of compute. But given that we already have R1 and DeepSeek did us a favor by putting this model completely open source, we have a much easier way of imbibing these models with reasoning, which is with supervised fine-tuning. So what you do essentially is you collect a bunch of questions, you ask DeepSeek R1 to give you the reasoning trace for those questions and also the answer, and you essentially just do supervised training on it, which is called SFT. So you simply learn from these reasoning traces of strong teachers, like DeepSeek R1, QuenWQuen, and these are super strong, so the model can really learn well. And why is SFT easier? To reiterate, it is much more compute efficient compared to RL, and it is much easier to get right. Because RL has a lot of moving parts, and it's a bit tricky to get the hyperparameters right. SFT, more or less, sure shot gives you a very, very good reasoning model. Now, I told before that we have a special thing in our model in which the same model can either be a reasoning model or a non-reasoning model. So we have the toggle to control the reasoning. And we do that with a simple system prompt. On top, we have system prompt detailed thinking on, and on bottom, we have detailed thinking on. So for the question, what is the capital of Canada? The model has different behavior. So we need to collect SFT data, which is similar to both of those cases, to have the model learn this kind of reasoning toggle. So this is where we describe the training pipeline for generating the data. So first and foremost, we collect challenging prompts. We collect challenging prompts both for reasoning training and non-reasoning training. In green, you have prompts for reasoning off, and in orange, you have prompts for reasoning on. You use DeepSeek R1 for reasoning outputs, and we use a bunch of different models like Llama, Qwen 2.5 for non-reasoning generations. But most importantly, we need to filter these responses for correctness. Not all the responses these models will generate will be correct, but we can invoke our cheap verifier to check whether all these solutions are correct or not. So we filter for correctness, quality, and complexity, and in the end, we get a lot of data. We have 1 million examples for reasoning off and 7 million for reasoning on, and this forms our final SFT blend, and we do our SFT training on it. Now, some of our key learnings from SFT were as follows. So this reasoning data is very, very information dense. Usually in SFT, you cap out with your performance at up to 1 epoch, but in reasoning SFT, we saw that training up to 3 epoch helps, all the way up to even 4 or 5, but for compute trade-off, I think 2 to 3 epochs is pretty good. Also, you need a much higher learning rate because you can see that it's a per token loss, and the number of tokens in SFT would be much, much lower larger in these reasoning SFT, so a higher learning rate also helps. On a side note, cosine decay also helps stabilize the training a bit. Now, we have a bunch of different reasoning benchmarks on which we evaluate our models, which even OpenAI and DeepSeek R1 does. Top 4 are some reasoning benchmarks. GPQA is a science graduate level benchmark. AMI 24, 25 are mathematical Olympiad. Live Code Bench is a competitive coding one. And bottom 3 are general domain benchmarks, which we still care about. Like BFCL is for function and tool calling, which is important for enterprise use cases. IFEVAL is about instruction following, where the model follows our instructions. And Arena Hard is for chat capabilities. So the interesting thing about SFT is that it doesn't just improve pass at 1, but it also improves pass at k. So pass at k essentially means for a given question, if a model generates k responses, what's the probability that at least one of those is correct? So pass at 1 means the first response that the model generates is correct. And pass at 64 means the model generates 64 responses, and only one at least has to pass. So you can see that consistently with more and more training, not just pass at 1, but pass at k also improves. So SFT doesn't just lead to entropy collapse or anything. It improves your pass at 64 as well. So these are the results for Super SFT. Now, 2 things to note. In gray, we have Llama 70B, which is the model we started from. And in light orange, we have the super model with reasoning on. The important thing was to not drop performance compared to Llama 70B, and more or less we don't. And then when we turn on reasoning, where we jump to dark orange, you can see across the board huge gains in performance with this reasoning SFT. Similar trend we see with DeepSeek with our Ultra SFT, where compared to Llama 3.1 405B, we don't drop performance with the light purple bar. And when we turn on reasoning, we see really huge gains in performance. Now, SFT will give you a very, very strong reasoning model, but it is still not enough. What if we do RLVR on top of these? RLVR starting from scratch is very compute intensive, but what if we could still do RLVR, albeit not for that long, but still get very, very good gains? So that's what we do. So SFT can get us close to the teacher, but not exceed it. So we have small models in the world, and we have large models. For small models, SFT is actually very, very compute efficient and very good because we are already learning from a very, very strong teacher, and SFT is easy to get right and very compute efficient. And it's also difficult to further improve the model with RL. But with large models like our Ultra, we have a chance to outperform that teacher. And for that, SFT will not suffice. We really need RLVR there. So that's where RLVR comes in. So this is, again, to recap, RLVR, we need a cheap verifier. Given a prompt, the LLM policy will generate a bunch of responses, and we verify, and then we use just reinforcement learning to drive this loop. Now, there are a bunch of different algorithms which people in community use. There is PPO, which OpenAI does, and there is GRPO, which DeepSeek pioneered. So let me give you a high-level loop of how GRPO works. This is a bit stripped-down version of GRPO. But essentially, the problem with GRPO was that it involved a value model. With PPO was that it involved a value model. Value model essentially is supposed to, given a response, judge that response. It's a language model, and it's very difficult to get right. So DeepSeek, with their GRPO, completely stripped that out, the value model. And in GRPO, what happens is, so given a prompt, the policy will generate multiple different responses for that prompt. So we call this a group. Let's take an example here. Like, we have x into x minus 1 equal to 0, and we want to compute the roots of this equation. Now, the model will generate 16 different responses, and then we have a verifier which will check whether the answer is correct or not. You can see only the last answer is correct, so we have these scores as well. Now, the important thing here is we compute this something called advantage, which is we normalize the rewards that each response got by comparing with the other responses in that group. So on top here, you can see the advantage for the ith response is essentially its reward, Ri, and then you normalize by the whole group. So simply, GRPO looks very, very simple. It is very similar to SFT. So this is the update equation for GRPO. The first part of the update pretty much looks like a SFT objective where you maximize the log likelihood of your response. But differently here, you also multiply it by the advantage. So you increase the likelihood of high reward completions, and you decrease the likelihood of low reward completions. So this is, in short, how GRPO works. The full GRPO has a bit more tricks. So there is a reference policy, KL divergence on the rightmost, so that the model doesn't drift too far away from the SFT policy. And there are a bunch of different tricks in which you have to, so in standard GRPO, you do one step of inference and then one step of update, but doing a huge inference batch at once is much more compute efficient. So what you do is you generate a lot of inference all at once, and then you do multiple updates, but then your policy becomes off policy. So that's why you need to do the PPO trick with important sampling weights. But yeah, for most part, the simple GRPO objective serves the purpose on a high-level idea of how this RLVR works. So our RLVR pipeline we specifically did for Llama-Nemotron Ultra with focus on scientific reasoning, code, and math, because those are good verifiable domains. So what do we start with? We start with a lot of reasoning data, around 200K. And this is just questions and the ground truth answers. So let's say for scientific reasoning, GPQA benchmark, we have questions and then multiple choice answers. So for a given question, we have the answer A, B, C, or D. But now what we need is we don't want to give the model just easy questions. Easy questions it can already do well on after SFT. So we want to first filter out and only keep the hard prompts. So for that, we actually use our previous model, Super 49B, because it's fast, to just rank all of those questions. So what we do is we feed all of those 200,000 questions to Super, and we see on what question Super 49B struggles with. And only for the questions in which Super 49B has a pass rate of less than 75, only those we keep. So we filter down the data by a lot, and we also sort our data. So out of those prompts, we sort them based on difficulty, and that's how we get our hard reasoning data, which is only 40,000 prompts. So now these prompts have questions and then answers, and then we initialize with the Ultra SFT model, and then we kick off the RLVR loop with GRPO. Now, a very interesting thing we did here is we did this GRPO loop with FP8 inference. So that's a bit tricky to get right. Everyone in the industry uses BF16 for inference with these loops, but at least in open source. But we did it with FP8, which increased it by 1.8x, the performance. So now for a reasoning data for RLVR, we have two ways to do it. Either we can do random sorting of the questions, or as I was talking earlier, we can sort these questions by the difficulty. So you can see that if you sort by difficulty, the model is much more sample efficient and it gets to a higher final accuracy. So that's what we adopt. Now this RLVR successful training run helped Ultra achieve near SOTA on GPQA. We started with an accuracy of around 66 on Llama-Nemotron Ultra, but this successful RLVR helped us catapult to a score of 78.4, which is right there with OpenAI models, so with Anthropic models, and just shy of the best models out there. So this shows you the real capabilities of RLVR, and it's tricky to get it right. We didn't get it right for other benchmarks, like let's say coding or math, as well as we did for GPQA. So this is where this model shines. Now the last stage is just polishing this model up. So one of the interesting things we saw when we did this reasoning alignment, reasoning SFT and RLVR is that the model becomes much less user-friendly. It doesn't follow instructions well. It's not as good for chat. So the general chat and instruction following capabilities deteriorate by quite a bit. So we have to polish the model up. So this is something which even DeepSeek R1 noted. So for making the model a bit better at instruction following, we again do RLVR, which I'll talk about. And for general chat capability, we use the RLHF paradigm using in-house trained reward models. So how do you do RL for instruction following? It's pretty simple, actually. Let's say, take an example. If we have a question like, write me a short story about something, and the instruction is generate at least 350 words, then verifying whether the model actually does that is very easy. You just check whether it generated 350 words or not. So you can, again, do RLVR here to recover the instruction following capability. Now for general chat capability, we use RLHF, where we don't have a verifier, but we have to estimate how good a model response is, and for that, we need a reward model. So reward model training is its entire different domain in LLM training. But we use custom in-house reward models, which are top of the leaderboard on reward bench, using our help steer series of models. So important thing to get RLHF with reward model right is high quality human data collection, which we did with our help steer 2 and 3 series, and careful reward model training. And then you can do your RLHF with DPO, GRPO, your choice of models. Now, another interesting thing we noticed was that these instruction following capabilities and these chat capabilities are also often at a conflict. So on x-axis, we have the IF-eval scores, which measures instruction following. And on y-axis, we have ArenaHard, which measures general chat capabilities. In x's, we have a bunch of different models we train. You can see that none gave satisfactory performance on both. So what we did was simply just merge the model to get a model which is good enough on IF-eval and maintains the scores on ArenaHard. Now, what are the results? In March, we released our Llama-Nemotron Super, so firstly, let's look at the light orange to the dark orange, which is the bump we get when we do RL. So this wasn't as successful a RLVR because it's a smaller model, but still we see some gain in a lot of these benchmarks. And in dark blue, we have QuenW Quen32B, which in its time was the best model in its weight class. So we outperform it in some benchmarks like AMI, et cetera, and on others, we kind of underperform. But the star of this release was the Llama-Nemotron Ultra, which was released on April 8, and back then, it was the best model out there. Compared to Gray, which is DeepSeek R1, we outperformed it by quite a bit in GPQA, and on other benchmarks, pretty much matched the accuracy. And you can see that compared to SFT, we do see quite a lot of gains. But DeepSeek R1 is still pretty good. Like, so why do we need Llama-Nemotron Ultra if you don't care about GPQA? So this plot kind of tries to answer that. Remember that these models are much more inference time expensive. So we need the models to be very, very efficient at inference time. DeepSeek R1 doesn't fit on a single node, so you have to do multi-node inference, and they're very, very slow. So here we have two different inference time settings. On blue, you have 5,000 input sequence and 500 output. There, Llama-Nemotron Ultra has a 1.9x the throughput, and in the other setting of 500/2000, we have 4x the inference throughput. So yeah, that's pretty much how we arrive at these models. I'll be happy to take any questions if you have.
Thank you so much for your great talk. I have a question about RLVR and the automatic verification. I'm curious about the methods that you use there and if any possibility to input your own custom verifier in that step.
Yeah, for example, let's just take the example of coding questions, right? So let's say you are given a complex code question, let's say competitive coding, and then the model generates an answer, and you have a bunch of different test cases. So a verifier essentially would be just a kind of Python function, just an execution environment, which will run the code which the model generated across these different test cases, and then you check whether the answer is correct or not. So in any domain, let's say in any enterprise case or in which you can kind of simulate that environment, so then you'll be able to do that RLVR.
Is it like string check type of verification?
So for some, it is string check. Let's say if it is just a mathematical answer, then it is just a string check. But in coding questions, the model actually generates a proper Python code, and you have to check whether that code is correct or not. And you can't do string check on that, so you have to actually run that in an execution environment and check whether for the test cases it actually passes or not.
And is it possible to provide your own custom function in that step?
Yeah.
Yeah, okay, thank you.
Thanks for the talk. One question with the RLVR, is the verifier output just a binary output? And if so, could you use like TPO and not have to go through like GRPO and worry about speed?
So usually it is not just +1 or 0. People do a bunch of reward shaping. People have tried to do partial completions, and then you try to evaluate those as well. But the most important bit here is to be on policy. Being on policy is very, very important. And with algorithms like DPO, etc., you may not be on policy. There are variants like online DPO, and they may actually work, but GRPO is kind of known to work as well. So, but yeah, good question.
Can you elaborate a bit more on what you did for inference differently than maybe what DeepSeek were doing? Why was your inference more efficient than?
So, okay, so let me just go back to this. I have to go quite a bit. So what we do is essentially, let's say if you have a transformer, let's say you have 16 different blocks. So it's kind of like a puzzle piece. You shrink down all of those 16 blocks into multiple different configurations. So you have like a local distillation for each of the blocks. You remove, let's say, some attention layers or some feed-forward layers, and then you try to see whether you can match the performance of that one particular block. So for each block, you'll have multiple candidates, and then you'll try to kind of puzzle it together, and then you can do you can optimize to find the right set, which will give you like really good performance and without decreasing the accuracy. But you will obviously lose on some accuracy. That's why we have to do some continued training with some distillation with the teacher to get that performance. Yeah.
Hi. One more?
Okay.
Yeah. When you're talking about verifying the results, it seems like you are verifying the final answer. Yeah. Like the code gives you some function, you're checking whether the function is correct. Do you verify the reasoning steps, so that the reasoning steps are valid? Or is it an assumption if the answer is correct, the reasoning to get there is probably correct?
Yeah, that's a very, very interesting question. We actually don't do that. It's possible that the model can be just faking the reasoning, but we just assume that if the answer is correct, that the model most likely would be reasoning right.